Okay, we're moving on to our talking about inner products. And I'm just going to talk about inner products in R2 and R3. By extension in Rn. You have two vectors. Let's say V1 equal X1, Y1. And V2 equal X2, Y2. Then the dot product is defined to be I'm going to put arrows over these according to the notation the book is established. You don't really need the arrow over these, but just remind us these are vectors and not points. Okay. Very simple. Just x1, y1 plus x1, x2 plus y1, y2. First coordinate times first coordinate, second coordinate times second coordinate. And it follows, actually the definition could be this. Okay. Definition could be V1 dot V2 is the magnitude of V1 times the magnitude of V1 times the cosine of theta. Okay. And this is connected to this very simply by the law of cosines. Your book will show you how that works. Okay. Well, what good is that? Well, example. V1, V2 is 2, 5, V1 is 2, 5, V2 is negative 3, 7. I can draw these. This is 2, this might be 5. Try to draw these to scale. So let's just say this is 2, 5. And negative 3 will be a little further over here, and 7 will be up about here. So here's negative 3, 7. Everybody write down what you think the angle between those vectors is. Then we'll calculate it. Now, if I do what we just talked about, if I sketch an angle, or a little line segment that's perpendicular to one of these vectors, so is the angle from here to here bigger or smaller than the angle from here to here? Okay. If you look at that, this angle or this angle? They look fairly close, right? I think one angle looks a little bigger than the other, but it's a little hard to see because you got this y-axis obliterating a lot of the, well, just kind of directing your vision. There's a bit of an optical illusion due to having this vector there, so let's get rid of it. Because now we've got a wet spot. Maybe a little easier to see. So which angle do you think is bigger? This one or this one? If you think they're equal, you're going to say the angle's 45 degrees. If you think this one's bigger, you're going to say the angle's a little bigger than 45 degrees. If you think this one's bigger, you're going to say it's a little less than 45. So give me another estimate. Nothing wrong with the estimates you made. Just try to connect with what we're doing. Okay, so let's just see what the angle is. According to this, the V1 is just how long the vector is, right? So that's just a Pythagorean theorem. And that's going to be the square root of 2 squared plus 5 squared. And this is square root of -3 squared plus 7 squared. And we're not going to estimate this right now, but that's square root of 29. This is the square root of 58. 58 is another roll, I think you can read it. Okay. Now, what's V1 dot V2? Okay, what's this thing? V1, magnitude of V1, and the magnitude of V2 equals the square root of 29 and the square root of 58. And now square root of 29 is about 5.4. The square root of 58 is about 7.6 or something. Okay. See, it's actually kind of easier if you multiply these numbers. Okay. Now I can multiply these numbers. Just, let's do 30 times 60. Okay, 30 times 60 is 1800, right? So 29 times 60 would be 1800 minus 58, right? So 1800 minus 58 is 1732, 42. Now, 40 squared is 1600, 50 squared is 2500. Okay, this is a lot closer to 1600 than it is to 2500. So I'm going to say this is about 42. That could be wrong. But I have some confidence in that estimate. But that doesn't always mean anything. Okay. Now, okay. V1 dot V2 is, by the definition, well, tell me, what's V1 dot V2? Okay, I knew you'd get it. No, we've got it. Okay, it's, by the definition, 2 times -3 plus 5 times 7, right? So what is the expression for cosine of theta? Well, cosine of theta, if you know V1 dot V2 and magnitude of V1 times magnitude of V2, you can easily find cosine of theta, right? So just tell me what the cosine of theta is as a fraction. Okay, so you're using your calculators, and that's good, because I was going to ask you to do that anyway, just to see how close I get. Okay, but taking this, it's pretty clear that that's going to be 29 over 42. If you have to get 42 over 29, you're just a little careless and solving this equation. You got to divide the dot product by the product of the magnitudes, right? And it's really, really easy to see that the dot product has to be less than or equal to the product of the magnitudes. In any case, there you have it. And that's 30 over 42 would be 5/7, which is about 0.71. Where am I? 7, 1, 4, 2, 8, and so forth. Okay. So it's going to be a little less than 0.71. I'm going to say around 0.7. It's probably 0.69 something. And knowing that the square root of 2 over 2 is about 0.71, that tells me that this is pretty close to the square root of 2 over 2, so theta is close to 5 over 4, which is 45 degrees. I think most of you estimated that this angle is a little bigger than this one, so, and I agree, it looks a little bigger. If I measured it, I'm pretty sure this angle would come out maybe 47 or 48 degrees. This would be the complement, 42, 43 degrees, okay? But that's my sketch. It means my sketch wasn't all that bad. If my arithmetic is right, it confirms that I actually sketched this pretty well, which is totally an accident, okay? So here we have it. Now you can calculate it more accurately. I mean, it's just, I'm going to take this one step further. Theta is just the inverse cosine of V1 dot V2 of the magnitude of V1 of the magnitude of V2. So go ahead and, if you got your calculator handy, go ahead and calculate it. Confirm that it really works. Some change of zoom again. I've come to a conclusion that happens when somebody walks in front of the camera. It doesn't always happen. I'm still trying to figure out just how you walk in front of the camera. The way I walk different than the way you walk. Is that the thing? Get some profound statistics, maybe even use some linear algebra to analyze it. Okay. Well, man, I understand all that. Camera on, but that's all right. I don't mind that being immortal. Okay, now bizarrely, I said it's close to 45 degrees and somebody keyed it in and keyed it in with all the information, because some people just use my approximations here rather than doing these square roots, okay? If you use the square roots, you come out with like 46 degrees, 46 point something, I think. Okay. And that's good. And of course, if you came out with a 0.8 or 0.78 or something like that, it's because you were in radian mode. Decide which mode you want to be in. For most mathematics, unless you're doing triangle trigonometry, you want to be in radian mode. And that's good. But degrees is more intuitive. And you're going to, if you do an estimate, you're not going to say that's about, oh, that looks like about 0.8 radians. No, it looks like about 45 degrees, give or take, okay? Well, anyhow, if you plug it in with these things, I looked at the calculator and it came out exactly 45 degrees, which is really bizarre. Okay, it shouldn't have done that. I mean, I won't say it shouldn't have. The probability that in writing down two vectors like this, that I'd hit one that's exactly 45 degrees is really, really small. Okay, really small. I'd say, you know, we just kind of hit the lottery on that one. Nevertheless, we can accept that. And we can also check, we could take a vector perpendicular to this. Okay, can anybody tell me how we would get a vector perpendicular to 2, 5? Okay, so yeah, somebody said, well, find the slope and do the negative reciprocal, right? Well, you don't actually even need to do that. If I want the vector over here, a vector over here is perpendicular, it's exactly that idea of the negative reciprocal slope. All I have to do is reverse these to make one of them negative, right? In this case, the vector would be -5, 2. It's perpendicular to 2, 5. Okay. Now, we do two things with this vector. We could then calculate this angle. And if this angle is exactly 45 degrees, then this is going to be exactly 45 degrees, right? Another thing, I haven't planned on doing this, but since we have that bizarre coincidence of that very improbable coincidence, apparently, what is what's that dot product? Okay, so you know, we're in a little bit of a digression here, but it's a good one. How do I know that this is perpendicular to this? Well, if you remember from pre-calculus and elsewhere that the negative reciprocal slope thing. Okay, but how can you be sure of that? Well, let's just see what do we get in this dot product? Well, that's clearly 0, right? That's it's -10 plus 10, but you know, it's obvious that these are the same numbers that these are, but this is going to be negative. So it doesn't matter. Which means now that we can prove that for any vector, if we reverse the coordinates and make one of them negative, vectors have to be perpendicular, right? So I'm just going to write that in here. That room up here. In symbols, that would be if I can write it down over here, it would be both this and this are perpendicular to DA, right? Okay. How do you prove that? Try to prove for me. Prove that. My statement is false. What's the length of this vector? That's the Pythagorean theorem. Square root of a squared plus b squared, right? This is not the square root of a squared plus b squared. Oh man, I'm not sure I recorded any of that. Let's see. So I'm going to say this real quickly, writing that down. Length of B is the square root of B dot B. And we can prove that. I'm just going to say because, but this is actually true. You could let B equal AB. Of course, implicitly B is in R2. Let B be AB equal AB. Then what's B dot B? B dot B is clearly A squared plus B squared. Are the details. And I didn't write down the square root when I first wrote this down. That was a bonehead error because I really did neglect to do that. I knew I was going to use B dot B, so that's what I wrote down. But it's got to be the square root because if this is B dot B, then the square root of B dot B is the square root of A squared plus B squared. That's the length of B minus the Pythagorean theorem. There you go. Okay. Now, what's the distance between the V1 and V2 vector? I asked you to write down that picture and show me where that distance would be. So I just want to see if you've got the idea, and I'll explain it a little more if you don't. Okay, distance between these vectors. Everybody drew a dotted line, okay? Now, the dotted line would most logically go between the tips of the vectors, right? Everybody had a dotted line. What dotted line didn't quite go between the tips, but there it is, okay? That's what we mean by the distance, because it's kind of the distance between these points. Each vector could be identified with a point at its tip. The vector is always rooted at the origin. Okay, so can we write a vector whose length is equal to this distance? In other words, if I want to represent a vector whose length is equal to this distance, all I've got to do is put an arrow in one end or the other. It doesn't matter whether the vector goes this way or this way, it's got the same length. The displacement would be better. Well, I'm going to do it backwards from the way most people would do it. Okay, we got this vector. Now, how can I express this vector in terms of V1 and V2? So call this vector U. We can see immediately from the picture, I dragged this out of you, we've only got about 7 minutes left and a couple of things to do. So, and it's usually pretty easy to drag things out of here, so I'm not too worried about that. We notice that V2 plus U equals V1, right? So U is V1 minus V2. Now, for reasons of convention, usually we do U in the opposite direction. But the distance will be the magnitude of U. So if this is a vector 2, 5, negative 3, 7, we can easily calculate components of this vector and find its magnitude. Of course, the magnitude is the dot product, if you remember to put the square root sign around it. Okay? And this would be the dot product of the reverse And that would be if the U vector went from here to here. Okay, well, there's distance between vectors. We understand what perpendicular vectors are. Okay, so I'm going to let you go. We just went over this, but after you leave, I'm going to just say it all again, so it'll be on the video. I think what we've got is a pretty good introduction to this section, and more than you probably need. I just said that we're repeating. And I'm going to get a little more formal in my presentation. Notice I kind of went to almost a theorem proof type approach here, because you need to see that, and you need to understand a bit about how to write these things out. And normally in the linear algebra course, we do a lot more with it. There's a whole lot of material that we need to cover here. So unfortunately, we're not going to be able to do too much of that, but I want to use that language so you get used to it. So you can also read the proofs in the book a little bit. I'll probably ask you to write out some simple things. Okay, so you can move on, and I'm going to just finish the recording. Recording something. Just, you don't walk in front of the camera anymore. Okay, just something that I didn't get to record last night. Okay, not sure how much of this got recorded. So here we go. This might be the second time you've seen that. But if you let U equal V over the magnitude of V, then the magnitude of U is 1. You prove that easily. Magnitude of U is the magnitude of V. The magnitude of the quantity V divided by V. Magnitude of V. Magnitude of V is just a scalar, so it can come out of the absolute value sign. And it's positive, so that's going to work. So you get magnitude of V over magnitude of V equals 1. So magnitude of U is 1. We say that U is the unit vector in the direction of U. There's only one. So for example, if you've got a vector of length 10, you're going to calculate U by dividing that vector by 10. So if its length is 10 and you divide it by 10, its length is going to be 1. Still going to have the same direction, because multiplying or dividing a vector by 1,000 quantity gives you a vector whose direction hasn't changed. If you multiply by a negative quantity, of course, its direction will reverse. And one other thing, magnitude of U, or I'm sorry, let V equal the vector AB. And I've expressed the vector as column vector. So this is now a vector expressed in matrix form. Of course, we're used to that with matrix equations like AX equals B. If I want to calculate V dot V, I can do it with these matrices by just doing V transpose times V. What's V transpose? Well, you know what that is. We switch the rows and columns. You have a column here, it's going to become a row. So here's V transpose, and here's V. Now, if we do matrix multiplication, we just do this row times this column. So we're going to have A times A, which is A squared, B times V, which is B squared. And clearly, if this vector had been expressed as x1, x2, x3, dot, 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 xn, then you can visualize what the transpose would be. It would be a row vector with the same components, and the components would still match up. So you would get x1 squared plus x2 squared all the way up to xn squared. And that's just an extension of the Pythagorean theorem into higher dimensions. If you extend the Pythagorean theorem into 3 dimensions, it's really easy to see that it works. If you have a vector with components A, B, and C, 3 dimensions, you can draw a rectangular solid and so forth and calculate and easily prove that the magnitude or that the length of the vector is square root of A squared plus B squared plus C squared. So Pythagorean theorem just extends easily. And of course, consequence of this, move around behind the camera, please. The magnitude of V is square root of Z transpose times.
Okay, good.